let's discuss using a video the same decoder 3 to 8 that we have in mind, and it is already solved using the plan A and B. Let's solve it now as another example of the plan C2, the structural and hierarchical one. The idea of inventing an internal architecture based on components of the same kind and something else, like logic gates organized in some way or another. So in the end, you will have, using this new plan, building based on building blocks, and signals and logic, a kind of a multiple VHDL file. And when you've got them all, the top entity, decoder 3 to 8, the one that you see here in this picture, and also the VHDL of the internal components and everything else, like the truth table of this logic circuit. When everything is finished, you can develop and synthesize and observe the RTL view to see if it's going to look like this, and then you can continue testing this device that you have invented using a kind of a test bench, always the same way. So that is another example for you if you would like to go practicing with this. Wait, let's design the decoder 3 to 8 using this time a plan C2, which is the one that in some way is related to the question, the conceptual question that we had seen there in the general concept map. And it is just like that, okay? How to enlarge circuits using simpler circuits of the same kind. We did that once for the multiplexer, designing a multiplexer of 8 channels using, for example, multiplexers of 2 channels and the like. So this time let's ask the same kind of question, because it doesn't matter, it's another standard circuit, so there has to be a way to do that. So this is the symbol that we have in mind, the decoder 3 to 8, and that's the table, okay? That's the table as usual. We place the inputs on the left side of the table, E, data 2, data 1, and data 0, and we left them go combining from 0, 0, 0 down to 1, 1, 1, 1, and in some way we at the same time organize the table so that it has meaning for us from the point of view of the functionality of the circuit. For example, if enable is 0, we can just string in the same row all the situations that means a disabled circuit, Data 2 doesn't matter, data 1 or data 0, that's not important, because if you like to disable the circuit, you want this kind of output, all zeros everywhere. And then if the circuit is enabled, depending on the binary code on the input, you get one hot code. And the one hot is this idea of, a single one at a time. If you have the number 3 in binary, you have a 1 in the column, the output Y3. That's it, okay? And the other outputs are 0. So this is the circuit that we like to design. In which way? Let's impose the constraint. Let's design, using the plan C2, that's right, which means using components and using multiple. In the end, the circuit is going to be a multiple file, okay, because we are going to use components. So let's impose this constraint. Components, decoders 1 to 2, for example. Here we have the possibility to choose decoders 1 to 2 or 2 to 4, in a way that some of them will be required to build this table. So what goes next? That's the key point. What goes next and how to proceed? Because this is the initial specifications, and this is again another specification that you are imposing here. Let's use this kind of decoder 1 to 2 as the basic component of the same kind, and that this is something that has this symbol, and this is the table associated to the symbol. It's like this, but a lot simpler. So what to do? Well, a way to start this exercise is, as usual, let's imagine that you have to fill a box, let's imagine that whatever we have in mind to design has to be uh, the architecture. It's the architecture of this large block that is the decoder 328, the binary decoder 328. So what is the input of this circuit? Well, what you see here, that is not going to change. E, enable, and data 2 is you like, data 1 and data 0. And then which is the output? Well, Y7, Y6, and down to Y0. That's the output of the circuit. Okay? So, how to proceed? Which is the idea here? Well, perhaps pay attention to the table again. Let's see if we can interpret the table or subsection the table in several parts. So, is it possible to identify this component in this larger table? So I guess so, right? Because this is only 2-channel wide, but here you have, you may imagine Y1, Y0, Y3, Y2, Y5, 4, and Y7 and 6 as if they were a couple of channels each group. So if this is what you have, you may imagine that this is your output, okay? Y1 and Y0, and you see 0, 0, 0, 1 and 1, 0. So here you are identifying this, and then there is only the possibility of selecting 2 codes. So this is the selection, 2 codes, okay? So 2 codes, so if data 0 is the D, you have 2 codes, you have an enable, so the same table of this smaller component is replicated practically here. You only have to think about this, okay? It's quite simple. And then, well, this is a mistake. I don't know why this is here, Sometimes when you write tables, I don't know, but it is zeros. That was what I was imagining. Here you have 0, except for the ones of interest, accordingly to the code 0 and 1. The other is 0. Is like if this device is disabled, okay? You see, this device is enabled up here, but then is disabled up there and down there. So if you think about the 2 outputs, these 2 outputs look like as disabled. Well, not used at all, 0, 0 everywhere. So this is for the, for this component here. Imagining that this is a decoder 1 to 2. So then what? Well, you can take another color and imagine the next 2, you see? You may imagine the 3 and the 2 outputs, and here is where the activity is placed. 0, 1, 1, 0, and then, so here the circuit is working. You may imagine that here, this new device is active, but in the other combinations of the table is disabled. So you see, how can you choose that 0, 1, 1, 0? Well, with the same line. So perhaps now you are imagining here 2 devices like this controlled in some way directly by the same data 0 signal. And the similar thing for the next 2 channels, 5 and 4, and another similar thing for the channel 6 and 7, you see? So, that's a kind of a way to go through this, of trying to imagine how this can be translated into circuits, because that is the idea of planning, inventing a circuit. So why not? This is a way, okay? So I can see now several of them. How many? 4. So, Y1 and Y0 of this device are going to be the the outputs. So I can very well now go and place those circuits here. This is the component that is going to be in charge of designing. This is Y1 and Y0. You have another one here, another one, and finally just another one down there. So Y1, Y0, Y1, Y0, Y1, Y0, and this is Y0 and this is Y1, you see? But this Y0 here and this Y1 is 3 and 2. So 3 and 2, and this is the same Y1 and Y0, but now this is Y5 and Y4. So in this way you have them all. Just placing decoders 1 to 2 at the output. So now it's time for, name them. So those are all of them. Decoder 1 to 2. Another one, decoder 1 to 2. So this is another one. Decoder 1 to 2. Decoder 1 to 2. So you have 4 of them. And what? Well, let me do that better, because it's no way you can do that better. This is Y0, Y1, very well. So this is the decoder 1, 2, because now let's reference every one of the chips. So this is, let's take another color. So this is the chip 1, if you like, the chip 2, the chip 3, and the chip 4. This is what you've got here. So now the inputs, you see, every one of them has the same input D, 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 and enable, enable, enable. So this is the component that you are using here, like this. And the D, it looks clear. The D is, I see that this is the one that will select every single chip 1, chip 2, chip 3, and chip 4. So it is quite like that. You see, you can connect all the Ds. The D is attacking all of them, and the D, is the D0. That's a kind of idea. Well, what is behind this idea here? This 0 is 0, 1, 0, 1, 0, 1, and it's doing the table of the simpler circuit decoder 1 to 2. And then what? Well, then here you have left 2 channels, or two lines of code, D2 and D1 and the enable, to finish it all. So in some way you have here the idea of input circuit, logic, you may call that logic, and the logic is taking the E and the D2 and the D1 as inputs. For what? What is this logic for? Well, for enabling this section, or enabling the other chip, or enabling the third chip on the fourth chip. So, the output of this circuit is going to drive, you see, every enable. That's what I see here, something like this. So now it's time for, well, let's use another color, because this is an internal wire. So it is good to get used to that, because you see, I rather like to do that again if necessary, just for the sake of keeping in mind that this is a port and this is an input port, because it's a straight connection to the input port. Very well. But then, the outputs of the circuit, better to be from another, taking another color. So this is the E, the E, the E, and the E. So this logic is going to generate, I don't know, E, how you like to call that, E4, you see chip 44, chip 3, E3, you see, at the same time that you are inventing something like this, you also have to name the signals. So this is E2 and E1. So E1, the wire E2, E3 and E4. So very well. So this is the E, D2 and D1. So this is the logic that if you can design such logic, well, you only have to place the gates here, the circuit, and it's going to work. Why? Because you have this idea in mind, but you see, this circuit goes accompanied by the truth table as well. So if you are thinking on the kind of a logic like this, you see, now is your turn for inventing. You see, you have to make room here. So it's your turn to invent the truth table of this circuit. Okay, logic circuit or whatever. So this is the truth table of the input logic circuit. Okay, and this is, I guess, three inputs. So E, D2 and D1, a double line, and now you see you have to forget about the Y's, but the output of the logic circuit, and this is E4, E3, E2 and E1. So now what is what you are pretending here? You have 8 possibilities, so let's well, for example, let's finish the table because we have that one as a reference. So let's imagine how this table is going to be, you see. So if enable is 0, I guess that this is not important because this is the general situation. You like to block them all. Them all means the 4 output chips of the same kind as the big one. So you will better generate disables here, you see. Disable signals. That way, that's clear. If the input of this circuit is 0, the outputs must be 0, so that the 4 of them are blocked. And so, if they are blocked, you have 0, 0 by default. You see, if E is 0, you have 0, 0 everywhere. So this is exactly what you like here. 0, 0 everywhere. So that is perfect. And then what? If you keep a 1 here, 0, 1, 1, 0, and 1, 0, 0, and then 0, 1, and then 1, 0, and finally 1, 1. Very well. So now you like that what? One of them works while the others are kept zeroed, are kept disabled. You see? So if this is what you have here, you like to drive the chip 0, 0 means in the end you see 0, 0 and 0 x, you know, d2, d1 and d0, because if this is what you've got, you have the y, you like to, you know, decode the code 0 and the code 1. This is what you like to do because 0, 0 is for the code 0, 0, 0 and 0, 0, 1. Okay, this is the third input here that goes straight to the 4 blocks. So now it is clear what you want in this table. Okay, you like something, you like to generate signals like this. The E4, that is for the chip 4. So this is, to make it clear, E4. This is driving E3, E2 and E1, you see. So 0, 0 is for activating the E1 because the E1 will allow this chip, you see, the chip 1 go on while keeping the others disabled as if you had input E equals 0. But that's the idea, you see. So now you only have to go doing the same. If you are now inputting to this block 0, 1, and then with another signal you generate the 2 and the 3. So yes, this is E2 exactly, and then this is the E3, and finally with 1, 1, 1 and 110, you are driving the outputs 7 and 6, which is down there, this. And so this is the chip E4, so the chip 4, right? The E4 goes to driving the enable input of the chip 4, so very well. So you have 1, 0, 0. So this is the table. And what is what you have to say now? Well, you know the circuit, you know the table, so very well now, because this is just simple logic. The next step, if you have a table, is to get the equations to translate later into VHDL in this top decoder 32A.VHD. You see, the top entity is going to be composed of 4 chips of the same kind and some logic, so very well. Which is that logic? The one that you see here. E4 is a function. You see, you are applying all the time the content of the previous project, so this time P1. So E4 is just this output function of the enable and D2 and D1, you know, this is the, and this is, as you like, max terms, min terms, product sums, but here it is very easy to imagine that E4 is nothing but this 111. So this is E, a single min term, the min term 7, you see, of this function. So this is the, you may write that very well, exactly as the min term 7, M small letter 7, and this is E, D2, and D1, exactly. So this is a simple AND, okay, of 3 inputs. So that's the circuit that you have to draw here, but you will not draw it, but write it in the VHDL in the end. So the E3 is something similar, and this is the only min term that the function have, you see. So this is just the min term 6 of this function, 110, so it is E, D1, and D0 not. Then you have the E2, which is practically the 5, so is E, D1, D0, okay, D1 and D0 not. This is, no, D1 not, D0, and finally E1, exactly the min term 4, which is E and D1, D2, or D2, this is D2, this is because D2 and D1, D2 and D1, D2 and D1, so this is the E1 is the min term 4, so it is E, D2 not, D1 not. That's the function. So you see it in the end is just a regular circuit as the others, quite simple naturally, because it's just an auxiliary circuit to drive what is required here, which is the enabling signals to control the way the output muxes are going to work. So this is a proper solution. And now is the time for taking another color and at least try one time or two to see if it's going to work later on when synthesized and applied into a instrumentation, you know, VHDL test bench, and to see if it's going to work for real. So what is what you like to apply now? For example, the number 5, who knows, just let's see what happens, and 1 in the enable. So if this is what you've got here, the solution of the problem has to be the vector, this 1, okay, this is what you like to test. Let's see if you have a 1 in the column Y5, keeping the others at 0, that is also very important. Okay, so let's see if this is true using this circuit that we have just invented now because we have imposed the condition of using decoders 1 to 2. So this is what I like to do, that test these stimulus, you see, 1, 0 and 1 in this structure. Well, if I apply this, I have exactly this line in the truth table. So very well, these logic gates down here are going to generate a 0 in the E4, a 0 in the E3, a 1 in the E2, you see, and another 0 in the E1. And what is the meaning? And well, the 1 is going to drive 1 here everywhere, and the D's. So the D has the idea of, driving the channel Y1, but this one is blocked. So here you have 0, 0, because the 0 in the enable has priority and blocks the code input. And here the same, so 0, 0. But here you have a 1 in the data, and then you have a 1 in the enable 2, right? Very well. So if you have a 1 in the enable 2, well, that circuit is going to be active, working, decoding, and this means that because you have a 1, you have a 1 in the Y1, and then you have a 0. I did it, you see. Let's try again, because you see you have a 1 in the Y3 while you are expecting a 1 in the column Y5, and this is why, because I've gone too fast here. In which way? Well, not applying the input 1 and the code, that is okay, but in the output generated here. Let me do it again, because it was something wrong here. So you see, that is why the idea of testing is for. That happens, you see. So that's good that this thing happens, because in this way you know very well what is the dynamic of the circuit that you have in mind. So let's do it again. So you see, what are you doing here is to applying 1, 1, 0 to this table, not what I said before. I was thinking here wrongly that the row that was in the case is 1, 0, 1, but that is not true, because this 1 in the D0 goes straight to the circuit, as I said before, you see. So this is 1, 1, 0. So it is this row that is the one that is driven. So very well. So this means that you have a 0 here, but now you have a 1 in the E3, a 0 in E2, and a 0 in E1. So very well. Now that's the same as before, but now it's going to work very well, because 0 means 0, 0 in Y7 and Y6. 1 and 1 is exactly what we like to be. 1 in the channel 1, because this is the code 1, and a 0 in the channel 0. And then, because those other signals are zeros, you have 0, 0 everywhere, because those circuits are blocked. So you see, you have what you want, the two table that is of your interest: 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So that demonstrates, at least for one vector, that you are in the right way. So that's what you do in paper, you see. So once you've done that in paper, the next step is, as usual, I will repeat that because it's the point of it. This is, you don't have to be afraid never to get to do what is next here, which is, let's translate this architecture into a VHDL file. So you know the circuit can be finished like this. So now let us translate the circuit to VHDL in the usual way, which is, let's find something similar, like for example the MUX8 that was invented using the same plan C2, or any other circuit invented using the plan C2. Let's take that as a sample and let's, adapt it, because it's going to be every section there. So you know the section of components, the section of signals. You have all the signals named, which is the right thing to do. You know all the equations that has to be typed in the text. You know the name of all the components, and then there is something else, guys, you see, going through this bullet list, You have it all except one thing. What is this thing? Right? Very simple. You have a job to do yet before going to the translation of this big structure. You see? And this thing is inventing. You see, you have to invent the component decoder 12.vhd. This is the component that you have to invent. Whatever the way, as a plan C2, it's quite, has no meaning at all, if you like, but you have to invent it. Whatever way, for example, using the plan B or the plan A, just take the simpler table belonging to a decoder 1, 2 and just draw the equations. So this circuit is going to be quite simple, but you need it. You need the decoder 122.phd. You need that before to proceed, because now once the component decoder 122.phd, and then you will need to generate this translation of the decoder 328 VHD, and then what you have to just generate a skeleton of a template and a skeleton of a test bench. So you will need later on the decoder 328 underscore test bench VHD. So you will use, you will translate at this stage another diagram to VHDL, but this diagram is going to be the stimulus of the circuit, like this 1 1 0 1. Just this, you are going to do that going to the internet and just copying or just typing some vectors, stimulus vectors in the template that's given to you by the the template VHDL test bench generator. So in the end it looks like that solution is a multiple VHDL file structure. You see the structure that we have designed. So it is this is the top, this is the component, and this is the test bench. So this is a story of 3 VHDL files that has to mix them all and compile them all together to synthesize the circuit. So in the RTL view, you have to see the circuit. Another story is what you see later in the technology view. In the technology view, I guess, that doesn't matter if you are inventing this way or equations, because the machines knows better what to do, which is the best way to translate such table into the resources required or available in the FPGA or the complex PLD. That depends on the manufacturer, tool, synthesizer, and the like. But you see, so that's another example of problem of this kind. So you can repeat that again, another video for another kind of decoder, that is for sure, the same way, or the same problem using other types of decoder. For example, variations, a decoder 328 using the plan C2, but imposing now the constraint that the component is going to be a decoder 224. So it's going to be quite similar. Instead of sectioning two columns at a time, you will go and section the big table in 4 columns at a time if you have a component which is a decoder 224. But the connections are going to be similar, and the idea of this input logic is the same. Okay, so that's an example, and we can continue here with the encoders and any other kind of circuit.